All right, it's 9 o'clock. Welcome, everyone. We're going to do a tutorial about introduction to IPython and Jupyter and how these tools can help you get your daily work done. There are three of us going to be presenting different sections. There's myself, I'm Min. I've been working on the IPython Jupyter projects for a long time, and then we have two other instructors, Matthias and Mike, over there. If you could raise your hand and so people can see you and they can help out. You can just, if you have an issue, you can just raise your hand and one of them will, or one of us that's not presenting will come help you out. So to get started, first you want to get the tutorial materials, which you can do. You can get the tutorial materials from GitHub. We are in fact going to do the tutorial presentation with Jupyter Notebook, so we'll be learning about the tool by using it. And to get started, you can download the repository with Git, or you can visit the website and download an archive with from the GitHub website with the download as a zip button, whatever you're more comfortable with. And then to get the software, as in the email that hopefully you got yesterday, you can install IPython and Jupyter with either pip or conda, whatever your preference. If you're using conda, you can just conda install IPython and Jupyter, and you can download conda from the Continuum website. The quickest way to get a really full-featured Python environment for analytics and science and computing is to download the full Anaconda distribution. So if you just Google Anaconda download, you can get started with Python with everything, and that comes with Jupyter and IPython installed. Or if you prefer to use pip for pure Python things, you can install IPython and Jupyter with pip. And before you install, as I would like to encourage the practice, and there will be a talk later by Matthias and others during the conference this weekend, but I would encourage anytime you're going to install something, the first thing you do is to upgrade the pip itself to make sure you're using the latest version of the installer, because it helps with transitions to Python 3 and things like that. So once you have IPython and Jupyter, and you have the folder called IPython in depth from the repository, in a terminal, you'll want to change into the directory called IPython in depth that you just created, and run the command Jupyter Notebook. And once you've done that, you should see something that looks very much like this. Just wait for everybody to get all set with that. And then just raise your hand if you have any difficulty getting the notebook running and open in the browser. Pretty good. Matthias? And while everybody gets started on that, I'll just give a bit of background on IPython and Jupyter. So there's, just to clarify, Jupyter grew out of the IPython project. So IPython's been a project that's been around for a bit over 15 years now, focused around just a better experience for interactive Python. And it started with just a terminal interface and with better tab completion and introspection. But it's grown, and we've added new features and new interfaces and new ways to interact with Python. And one of the things we did was this notebook that we're looking at right now. And when we built the notebook, one of the results was that the notebook was actually useful in languages other than Python. And so people started using IPython notebooks in Julia and R and Scala and other languages. And so we decided that the Jupyter part of the project, or the notebook part of the project that wasn't Python specific, needed a new name. And so the IPython notebook got pulled out of IPython and became a standalone project called Jupyter. And that's the relationship of IPython and Jupyter. That Jupyter is kind of a new name for the parts of IPython that have can be used outside Python. And so the first part of this tutorial, we're going to talk a little bit about this notebook application first, and then we'll go into IPython specifically and how IPython improves your the interactive experience of working with Python. So if everybody's all set with their notebook dashboard, the notebook I'm starting on right now is this index notebook. So you can click that and you'll get a table of contents showing kind of the rough outline of what we're going to cover today, with links to the notebooks that we're going to be using. And we're going to start out with this notebook basics, where we'll see a bit about the notebook application and how it works. So if you click that link, you should see a notebook titled Notebook Basics. And we've all gotten started with launching the notebook by typing the Jupyter Notebook command at the command line. And this takes a bunch of options that you can use to control how the notebook runs. But by default, when you run this command, it automatically opens a browser pointed to the notebook web server, and the notebook application is itself a web application. So all the UI runs just in your browser, and then the notebook is a web server serving files and running code. So the different pieces of the notebook application. The first piece you'll see when you start the notebook is the dashboard, which has the list of files that you can work with, and you can have different files. You can have notebooks, but not just notebooks. You can also work with text files and others. And if you look at that dashboard, you can see that you can check boxes, and when you check boxes on items, you can see different actions available to perform actions on those files. So I can say select this file, and I can make a copy of it by saying duplicate, and then yes, I want a duplicate of that. Now I've got a copy. I can rename. And then you can also click edit to open files in a text editor. Oops. And so normally you've got this, and you can browse into folders by clicking folders, and they'll just open a new tree view. And you can, up here with the breadcrumbs, you can navigate up to previous directories. So we're working with this Notebook Basics notebook. And another tab in that dashboard next to the file list is the running tab. And that tells you what is currently running. So when you open a notebook, it starts what we call a kernel, which is a process where your code runs when you actually type code and ask to execute it. And each notebook that you open gets a different kernel. So when you run code in one notebook, that's running in a different process when you run than code in another notebook. So if you create figures, define variables, those are all available in that one notebook. And then when you use a different one, then you've got a different namespace, different process where everything is running. And because these notebooks can be in all kinds of different directories, there's this convenient list of currently running notebooks. So I can see here index is it's green because it's running, and you can see there's this little running label, and you can see when it was last modified. In this case, about an hour ago. And you can sort this list by last modified date if you want to see, what are the most recently edited files in this directory and things. And the next part where we'll focus most of our attention is on the notebook itself. So when you click a notebook from the dashboard, you'll get a view that looks like this, where you have, if I don't hide it, you'll have a document-style view of the notebook document itself. And then you've got a familiar kind of file edit view menu bar that you can click and perform different actions. And a useful thing here is the user interface tour that gives you can open this to take a little tour through the notebook interface. And we can see that in the toolbar, in the header here, we can see the file name. This is the name of the current notebook we're working on. And if we click that name, then we can change the name of the notebook. And then you can see some whether there's unsaved changes or whether it's been when it's been changed. And then the main part of the notebook is this document area where where a notebook is a sequence of what we call cells. So each segment of the notebook is a cell of one of a few kinds. So this notebook is composed just of markdown cells, where each of these cells actually contains markdown, which is then rendered to HTML. But when you're running code, then there will be code cells where you can type code and see their output. And then there's another cell type that's for more advanced usage that's called a raw cell. That's used for a tool that will be talked about later called NB-convert, where you can type some LaTeX or some other format, and then that code will get passed through to an export file. But we won't get into things that advanced today. So when you're working on a notebook, the notebook has what's called a modal interface, and so there's two modes when you're working with the notebook. When you have a blue border on the cell, you're in what's called command mode, where if you start typing, what that's going to do is actually issue keyboard shortcut commands. So there's no modifier. So if I wanted to cut a cell, I would just press X instead of Command X. If I wanted to copy a cell, I just press C instead of Command C. And there are shortcuts for navigation, for moving cells around. And then to enter edit mode, when you want to run some code or edit a markdown cell, when a cell is selected, like this one, we can press enter, and that enters edit mode. And now we have a green border, and we can actually edit the contents of this cell in markdown. So I can type some italic. And then we can leave edit mode by pressing escape. And then you can re-render the cell by pressing shift enter. And what shift enter does is it takes a cell, and if it's a code cell, it executes it, and if it's a markdown cell, it renders it and selects the next one. So you can select cells by clicking on them, scrolling around. You can select multiple cells by holding shift and clicking adjacent cells, and that lets you select a group of cells and move it around in the document. So for instance, I can select this cell and this cell, and I can move it up and down in the document with these arrow buttons here. And in command mode, you can navigate through the document with the arrow keys, so just select the next cell by pressing down, select the previous cell with up, and you can execute if I had a code cell, so I did create a new cell above, and this is now a code cell. You can press the little play button to execute that cell. So if I put the code 1, then I can press this little play button, and it will execute that. And you can see the result is 1 there. And with there are a bunch of keyboard shortcuts that you can use in this command mode. And the way you can see those keyboard shortcuts is in the Help menu. You can click Keyboard Shortcuts, and that'll show you all the shortcuts in edit mode and command mode. So you can change the cell type to code, to markdown. You can cut, copy, paste, save, etc. And then there's some keyboard shortcuts in edit mode with modifier keys. So some common shortcuts that are, there are lots of keyboard shortcuts, and you can even customize the keyboard shortcuts to, in Notebook 5, you can customize the shortcuts to suit your preferences. But common keyboard shortcuts that for really common operations that are good to know are A and B for creating a new cell above and below. So I can select this guy, and I can hit A to create a new cell above, and I can hit B to create a new cell below the current cell and keep creating cells. So these are useful for quickly creating new cells. And then you've got cut, copy, paste, etc. And the standard keyboard, standard shortcuts just without modifiers. So X for cut, C for copy, V for paste. And then we have keyboard shortcuts for interrupting execution with I for interrupt, and period for actually restarting the kernel. Now, the Notebook web application is not just for editing notebook files. There's also the text editor that we saw. So if we open if we go to the tree, we can say, click this new button, and you'll see you can create a notebook, and each notebook is associated with a different kernel. And so you'll see a list here of all the kernels you have installed on your computer. And you can install kernels for Python, for Julia, for R, for Scala, for Spark, for C++, for any of a number of languages. And when you click one of these, it creates a new notebook. But you can also create things that aren't notebooks. So you can create new folders, or you can create a text file. And if you create a new text file, that will open in a full-page plain text editor. So this is, I've got untitled.txt, but maybe I want it to be test.py. So now I've got a Python file, and I can write some Python code. And then the last piece, yes? Mm-hmm. Mm-hmm. Yeah, so the question is about what's the workflow of saving and kind of how is it talking to the server and working with files. So it's really just like working with plain files. So when you save, it's just writing a file to the disk. So doing things like working in a Git repository and writing commits and everything is handled as a separate activity. So it's just like opening a file in your traditional text editor or IDE, and then saving that to disk, and then doing version control operations separately. So it's not doing anything special in that regard. It's just creating files and modifying files on disk. And when you're running, well, it happens to be a web application with a server. The way we're running it today is, it really is, you can think of it as a local desktop application where the interface happens to be in your web browser. So you're just editing files on in your home directory on your local disk. So there are hooks. The question is about, are there hooks for doing more actions on save and things like that? There are hooks in something on the server called the contents manager that implements this saving and opening of files, and you can register additional actions to be called on save, which could do things like create new commits in a repository, add files to a repository, that kind of thing. So there are hooks to enable that kind of thing, but they're not. There aren't any hooks enabled by default. And so the last piece of the Notebook web application, which isn't particularly useful for the local case because people have a terminal, but because the Jupyter Notebook is a web application, it can be used to expose remote computing resources. So maybe it's running on a hosted server as part of company infrastructure or campus computing resources for a course, and it may be your only window onto the machine. And if that's the case, then you can start terminals on the Notebook. And this does require that the server is running on a Unix machine, Linux or Mac OS. This one feature doesn't work on Windows. But if you create, say, a new terminal, then what you get is a familiar terminal interface, and I can do things like ls and git status. And so you can do, if you're doing work with notebooks in a Git repository, you can use, this would be where you enter your Git commands for creating your commits and things. And this is a full terminal, so you can run things like VI, Emacs, and all those fancy things. Yes? So the interface of the terminal is running in the web browser. There is an actual real PTY running on the server. So these are actually the files on my file system, but the UI is, you can see this just is my Safari browser. So this is just another web page exposing that terminal. So this lets you have a terminal in the kind of remote notebook case. This lets you have a terminal accessing a machine without having to do things like SSH and deal with that kind of stuff. And back to our index. We're going to get on to running some code. So we're going to open the Beyond Plain Python notebook. And we're going to actually get into, so that was kind of a bit of an overview of the Jupyter Notebook application and how it works and what pieces there are to it. And now we're going to get into using the notebook with IPython to actually run some code. And so the first thing is we select our first cell with a bit of code in it, and then we can press Shift-Enter to execute that cell and select the next one. Yeah. This one, if you go back to the index, and you click IPython Beyond Plain Python. And I'm going to clear all the output from this notebook, just so that we can see the results as we're making them. You can say you can print some text. A lot of IPython's extensions to Python have to do with introspection and getting help and figuring out what you want to do. So a lot of the time when we're doing interactive computing, we don't quite know what we want to do. And maybe you know that I want to use this library function, but I don't know quite how to call it. I don't know what exactly what it does. And a lot of IPython is built around asking questions of your data, asking questions of IPython itself. And most of these things are implemented around the question mark, which is something that IPython adds beyond what the Python language gives. So the most basic question you can ask is just, tell me something, I don't know. And so if you just type question mark, you'll get some output that tells you about IPython itself and the how to get help, where to get more information, what can IPython do, what's IPython for, and then a quick tour of the kind of information that we're going to go over today. So kind of when in doubt, question mark. Yes? Yeah, so there's a thing called the pager, and there's some configuration for whether output that would go to the pager should be produced as normal output, which is what I have here, or it might show up as a pop-up from the bottom. And that pop-up is called the pager, and it lets you kind of see help output and still scroll around in the notebook, but that's just a display preference. So that will give you some help about kind of how to use IPython, the various things IPython can do, and where to find more information. The first thing that we'll do most often with IPython is say I have an object, in this case the named tuple type from the collections module, and I want to say tell me something about that object. And so if you type a symbol in your namespace and you put question mark after that and then you execute, you'll get the signature. So now you know how to call named tuple, and then you'll also see the doc string for any documentation that the object has about itself. And this really helps for you're using some library, NumPy, Matplotlib, Pandas, and you want to use you want to instantiate one of these objects, or you want to call this function, but you're not sure what the argument order is, or you're not sure what flags are available to steer that, what options are available to you. Question mark can give you a really quick reference to answer those questions that may not be without having to open separate documentation and deal with switching back and forth to different contexts. So in this case, I can create a name tuple, you give it a type, and then you give it some fields, and then there are some keyword-only flags. And then there's some examples for how to use it. And now if you want more information, so that was question mark. If you want more information, you can give it an extra question mark. Just say, tell me more. So if we do that, again, instead of showing just the doc string, we actually see the source code for the file, for the object. So I wanted to look at the collections counter class, and if I give it 2 question marks, I actually get the class definition. So I can see there's the doc string there because that is attached to the class. But I can also see actually how the init method is defined. I can see that counter is a subclass of dictionary. And then I can see what methods are defined on it, such as the most common item, the most common items in the counter. Give me the elements of the counter. This can be useful for inspecting. Maybe you've got a function and its doc string doesn't provide enough information to tell you what it does. You think you understand what's going on, but it doesn't do what you expect. You can just peek at the source code of an object or a method and see exactly what's going on. And this can be useful for the kind of poking around exploration in IPython. And then the next use of question mark is with these wildcards. So here I've got asterisks on either side of int, int, and then a question mark. And what this does is it searches the current namespace for any symbols that match that pattern. So in this case, it tells me that I've got the built-in function print, int, and I've got the floating point error. And now this can be useful for maybe a module that has a really big API and you want to find where a given, find all the functions associated with something, or you kind of remember the name, but you don't remember exactly what it is. So an example, I can import NumPy, which I know NumPy does a lot of things with arrays, but maybe I don't remember exactly what method I want to call. So I can say, show me everything in NumPy that has array in the name. So I can see I've got NumPy as array, array equals rec array, and so this lets you do things that are more than just tab completion, which only match a prefix. It lets you say, show me everything that mentions array, or everything that starts with array or ends with array, that kind of thing. And then, like the question mark, we've got a quick reference, so just a little helper card to show you the kinds of common actions you can do with IPython to get a quick reminder for when you're getting started and trying to get used to what IPython can do for you. The quick reference will show you, okay, I remember question mark, I remember the wildcards, and then the magics that we'll get to in a bit. Tab completion is an important part of any interactive interface. So when you start typing some text and then you press tab, if there's only one match, it will automatically complete that text. And there's attribute completion. So I'm working with the collections module, and I can press tab, and it'll show me all the attributes on that collections module. And I can just use the arrow keys to select a match, and I can type. Once I've opened the tab, I can start typing async generator. And this is useful both as a kind of poking around tool. So we mentioned the NumPy .array. So like this lets me do poking around like that wildcard match, but this lets me do prefix, kind of as you type, poking around. And it also lets you kind of see what attributes an object has. So I've created a variable I, and I can do I.tab, and I can see all the methods on that object. Like I can get the conjugate, I can get denominator, imaginary part, real part, etc. When you're doing interactive execution, so each one of these cells is a what we call an input. It's a code that you've asked to run, and each input has an output. So you can see on this left where it says in 11, that's input number 11, and that counter goes up as you execute more and more code. And that's not necessarily related to the position in the document, although if you run them from start to end, they'll all be in order. But because this is an interactive session, I can go up and down and run things out of order. So that's output 11, and I can run another cell, and so output 11 is below output 12. And if I run this again, those will get different numbers. So each time I run this, the number goes up. The previous output, this is most useful when you're using IPython in the terminal. When you just type IPython in your shell, you can get the previous output is referenced by the underscore variable. So every time there's an output, we can reference it by the previous result as underscore and add 10 to it. Since I've just run this cell is now the most recent output, and if I run it again, it will add 10 to that. So we've got 12 and now 22, and I can keep running that, and it'll keep increasing by 10 because it's getting the output from the previous execution. And that's specifically the previous execution, not the previous in time, not the previous execution on the page. So when you're running code that's not tied to what it looks like in the document, it's tied to actually the time order when you're actually selecting cells and executing them. Yes? Yep. So the question is about intersecting with the terminal and the relationship with environment variables. So I will peek ahead a tiny bit. And so the notebook server itself is just a process that started on your machine. So it has environment variables defined. When it started a kernel, that kernel was a subprocess that may have gotten environment variables added to it. And it will also inherit environment variables from the notebook server environment. And so if you have, so in Python, you can access environment variables from the OS module. So if I look at dict os.environ, we can see these are the environment variables of the process. And IPython has what's called a magic, where I can type %env, and that gives you the same thing in a little shortcut. So it's not that common. So there's, for Python, things to be influenced by environment variables, but those that are, they'll be available and defined and have the appropriate behavior in IPython, just like they do in a normal shell, both in the terminal and in the notebook. Some calls have expressions have an output that you don't actually want to see. So maybe you've got a cell that you end the cell by doing a function call, maybe that plots, and that function call returns something that you're not actually interested in. You can suppress output by putting a little semicolon on the end of the line. So here I've got 10 plus 20, which would normally output 30, but if I put a little semicolon on there, then it actually won't show me the output. But it does still store the output. It only doesn't display it. So the semicolon suppresses the display of the output, but not the storing of the output. So if I look at what or it does suppress the storing of the output. So if I look at the previous output, that's this environment dict there. And then you've seen the little out guy over on the side. Those are available as Python variables. So out with a capital O is a Python variable that's a dictionary with integer keys. So I can see what out10 is, and there's also a shorthand variable with the underscore. Maybe 10. This is what I get for executing out of order. I'll go with 11. And you can see what out11 was. It was 12. That's this guy up here. And then we also have, so the outputs are cached with this out variable, and the inputs are also cached with this in. So each bit of code that you ask to execute is available in a dictionary called in. Actually, in might be a list, where you can access the blocks of code that you've run before, and you can modify them. And you can see the most recent input with just underscore I. It's like, what was the last thing I executed? And then we have these magics. So magics are something where we extend the Python language with these percent characters. So if you start a line with percent, that's going to call the rest of the line, in this case, this -n 1 to 5. And it will show the IPython command history for items 1 to 5. And the magics are another thing that IPython provides that extends the behavior of the Python language and gives you new convenient functionality for kind of common operations that are possible to do in Python, but often might be tedious, like cd. You can just type, just like you would in a shell, you can type cd to a directory instead of having to type out like os.chdir, etc. And so as a quick exercise for knowing that percent history will show you the IPython history, and knowing that we have this question mark tool for poking around and learning about about objects and functions, a little exercise for putting those to work is see if you can figure out how to, with the history magic, write the last 10 lines of your history to a file called log.py. Underscore I is the most recent input. So this is the most recent input. You said underscore 11. That is output number 11. So underscore 11 is shorthand for out 11. And underscore I is for input. And you can see there's actually I 11. So I11 and 11. You can see are the input and the output number 11. And a lot of the kind of terse features, like these underscores, are from IPython's terminal interface, where saving characters is really precious because you're typing everything out anew all the time. A lot of these things, the more terse synonyms for something, we don't use so much in the notebook because typing out characters is not as costly in the notebook. Yes. Yeah, so the question is, how do we manage overloading special variables? In most cases, we don't. Just like in Python in general, you can use those variables to define things yourselves. For the most part, we'll define those variables, but we don't interact with them. And so you can override those functions just like you can override the print function. And that will generally be fine. It's just that the IPython variable won't be available to you because you replaced it. There are a couple where IPython interacts with those objects, like out, where I think if you override out to something, IPython will complain as it tries to put new items into it. But for the most part, it'll just be fine. You're defining new variables. So the first hint on this exercise is that question mark is the key to finding out new information. So if I do history question mark, I can see the docstring for history. And then this is an exercise in reading docstrings. So what's my task is I want to write the last 10 lines, and I want to write it to a file called log.py. So what I'm interested in is, okay, how do I tell it to get 10 lines instead of 5? And how do I tell it how to save that to a file instead of outputting it to my terminal? Well, we can see we've got -f. We'll say instead of printing the output to the screen, send it to a file. Okay, that's part 1. And then -l with a limit says get the last n lines from all sessions. The all sessions thing is because IPython saves your history from each time you use IPython, it creates a new session in your history. And so IPython stores your history of commands for not quite forever, but for a very long time, up to 10,000 commands or something. So you can search through your history of commands for the past couple of years and say, I know I did some complicated plotting call. I don't remember exactly how I did that. Let me search through my command history to figure out, to try to remember what the exact right incantation is for this complicated library. So based on this information, I know I want history. Limit, I want the last 10 lines. So limit that to 10. And then I want to save it in the file log.py. Do I want to overwrite? Yes. And make cat. You can see the not especially interesting commands because I was demonstrating the input-output caching most recently. Only this session? Yes. So if you do by default, when you just type history, it will give you your whole. This is my whole session. So that's actually the default behavior, is show me this entire session.
Yeah, I can put you said that it collects your sessions across time.
Yeah.
And then -L looks at all those sessions. So if you've done this, add multiple sessions,
Mm-hmm. No, so it's 10. So it's 10 lines going back from the end of this session to the beginning of this session, and then to the previous session. So yeah, yeah. So it's not going to do the last 10 of every session. It's the last 10 commands, and it will cross sessions if you asked for more commands than you've executed this session. And then there's a little query syntax for specifying which session and which lines in that session. If you want to say, show me, 2 IPython sessions ago, the first 5 commands, that kind of thing. Yes. Yeah, so this notebook is not next to the index notebook. So another feature of so we've got these notebooks distributed throughout folders, and the notebooks in this tutorial are in these subfolders by category. So there are a lot of resources in this tutorial that we won't cover today because it's enough material for 3 to 5 days of teaching. So I encourage you to check out the repository and poke around with the stuff that the more advanced things that we don't cover today. But when you open a notebook, the kernel, the process where that code actually runs, will start in the same directory as that notebook file. And so since this notebook file, that's perfect lead into the next thing that we're running. If you start a line with exclamation point, what that will do is execute a shell command. So in this case, I'm executing the shell command pwd for print the current working directory. And we can see that we're inside the repository in the examples subfolder and in the IPython kernel subfolder in there. And so if we yes, so this is just calling out to your shell. It's really just calling out to os.system. So if you're on Windows, you can do bang dir and all the Windows shell commands. And if you're on Mac OS or Linux, then you've got all your Unix shell commands. pwd happens to be a command that is the same on both, I believe. And if we do, you can store the output of these shell commands. So here I did files equals bang ls, which is say, run this shell command ls and store the output in the Python variable files. And then I can print the current files in the current directory, and then I've got a Python variable. And what is that? It's a list. It's a Python list where each item in that list, it's, okay, Matthias is shaking. It's approximately a Python list. You can treat it as a Python list. It's more than a Python list. It's a Python list with some fancy convenience features. And the each item in that list is a string that is a line in the output of the command. So if I did bang ls here, you can see each item in this listing, and you can see each item in that listing is one of the entries in that files variable. So that lets me get the output of shell commands into Python, but we also have the other direction. You can also get Python variables into your shell commands. This gets you kind of a fancy shell scripting environment with access to a lot of Python features. So I can do !echo, which is just the echo command, but then I can give a $, just like you would do for an environment variable in a shell, but I'm going to give it files, which is a Python variable, not a OS environment variable. It's just a Python variable in my current namespace. And what that does is it replaces the string $files with the string representation of that variable in my current namespace. And you can also use Python string formatting. So if you put something in braces, then in those braces you can put any expression, and that expression will be evaluated in the IPython namespace, and then that's the string that will be assembled onto the command line that gets executed. So in this case, I want to say, give me the first item in the files list, and then make it uppercase, and then pass that to echo. Right, so then I'm echoing the first file in uppercase. And these kinds of operations don't have to be on whole files of their own, whole lines of their own. They can be, or they don't have to be in whole cells of their own. They can be kind of in arbitrary nesting structures. So I'm iterating through the files. I'm saying if that file is a notebook, then echo the index in the list, and then the base file name without the file extension. So this is mixing Python formatting, shell execution, and Python iteration and logic on all together. And then if it's not a notebook, just give me just a little doo-doo. And there we can see, in order, we get the titles without the file extension, and then we get just little placeholders for all the files that aren't notebooks. So the last and biggest extension that IPython makes to the Python language is this notion of magics. So we saw a little preview of magics with history. A magic is anything that starts with this % in IPython. And just like we did with question mark, the first magic that we look at is the magic called magic. And what magic does is it tells you about magics. So if you do %magic, it tells you about what magics are, how they work, some common magics, and in fact, a huge amount of information about every magic currently available in IPython. Ultimately, every magic is just a Python function, but instead of that Python function taking, being called with Python objects, it's a Python function that will get the first kind of magic is called a line magic, so it starts with 1%, and then followed by the name of the magic, and this one called timeIt. And then what this gets is the rest of the line as its one and only argument. And then that timeIt function is responsible for interpreting that line as something, and then taking some action with it. And so the timeIt magic, which is particularly useful in IPython when you're doing profiling, when you're doing little quick performance analysis, of what it does is you give it an expression or statement on the right-hand side, and it runs that and then tells you how long it took. And this functionality provided by the Python standard library in the module called timeIt. But using the Python module timeIt requires a bunch of explicit arguments, and you have to tell it how many times to sample and how often to run. And the timeIt magic just adds some heuristics to do that, to pick a sensible number of loops based on how long it takes, so that you can do this really common task with a bit less typing. So what timeIt does is it takes the expression, it runs it once, figures out roughly how long it takes to run, and then it does some statistical sampling of, okay, that's a really fast operation. I'm going to run it 100,000 times, and then do some metrics on that. And if you time something that takes a lot longer, it might only run it once or 10 times, because it doesn't want to do a timing that'll take 3 days. So in this case, it's creating this list of 1,000 elements takes about 15 microseconds, give or take 1 microsecond. And so that's line magics, which get the rest of the line as their argument. Then there's CellMagic. So we started with 1% for line magic. For CellMagics, we start with 2%. And just like the line magic, the CellMagic gets the rest of the line as an argument if there's anything there, and it gets the rest of the cell just as a string to interpret however it wants. And this lets you do things like, in this case, time. You do the same timing for the entire contents of the cell, but it also lets you define, in this case, the rest of the cell is Python code like a normal IPython cell, but it could be there can be any arbitrary interpretation of that string. So there are, for instance, SQL magics where you write just a cell full of SQL and it executes those queries against a database. And there are magics for R and Julia that actually execute R or Julia code and send data back and forth from your Python interpreter, and can do arbitrarily fancy things with these guys. Line magics can be used in code blocks, just like we saw with the exclamation point for shell escapes. So you've got a for loop, and what I want to do is create ranges of various sizes, and I'm just going to iterate through a number of sizes, and then time how long it takes to create those lists, and then it will pick the number of loops based on how long each one takes, which are very similar. But you can see that once I crossed a threshold of 2 microseconds, it switched from a million loops to 100,000 loops to keep the total time within a reasonable range. And so, because CellMagics can have this arbitrary interpretation, one useful application of these CellMagics is calling out to other shells. So there are a lot of scripting languages you have on your computer. There's a good chance you have Bash, Perl, Ruby, R, etc. And you can, IPython finds several of these shells and registers a shell magic for each of those. In this case, Bash, where the code I'm writing here is not Python code. This is code interpreted by the Bash shell. And then when I put %% bash, that says, hey, IPython, instead of executing this code yourself, take this code and actually send it to a Bash interpreter and execute it there, and then capture and display the output. Right? And another example of a CellMagic, which takes both a line and a cell, is the write file magic. And what this does is it takes, on the line, you pass it a file name. So I want to create the file test.txt. And then the rest of the cell is just the content of that file. Right, so this is useful in tutorials sometimes when I want to say, okay, I've got this tiny file on disk. Rather than opening up another tab and saying, look at this file, I can just say, I'm actually going to create the file right now. So what this does is actually created the test.txt file, and then I can look at the contents of that file. And then to finish it up for future reference, there are lots of magics that come with IPython. There are also lots of extensions to IPython that let you register new magic. So ultimately, a magic is just a Python function. And you can, there are extensions to IPython that say, add this new magic. So the SQL magic is not part of IPython. It's a separate package that extends IPython and gives you these new magics. The Cython compiler has magics for doing inline compilation of Cython extension code, which is really handy for profiling and prototyping extension code. And there are lots of these fancy magics for getting a new custom functionality into IPython. You can write magics yourself for common operations that you happen to do a lot that you want to make more convenient. And you can register those with your Python installation by default. So LS magic just gives us a quick listing of all the current magics registered in IPython. So I can see I've got these HTML and SVG and history and all these magics that we haven't used, but that you can explore on your own time.
Question.
Yes?
Is AutoMagic simply on? That's how you avoid having to do these.
AutoMagic is on by default. That means I can do things like, what did I just do? Time it. Time.sleep. Yeah, so you don't have to, and this is a preference that you can turn on and off. So you may or may not need to. So I can do the AutoMagic magic toggles whether magics are automatically executed. So if now that I've turned on AutoMagic and I do that, I'll get a name error that AutoMagic isn't defined. But if I turn it back on, and then I can execute it, and it will turn it off. And now it won't work anymore. So that's just a save a character kind of thing. Sometimes documentation will have code in a form that it looks like a Python, interactive Python or IPython session that has these prompts on the front. And so this is something where often you'll have documentation that has, here's some example code, and this is what it looks like in the terminal. So it's got actually the prompts. And so if you just select the big block and copy it, it will include prompts like this. So this is not valid Python code, but IPython knows that this happens all the time, that people grab a snippet of code from documentation, and I just want to copy that and paste it. So IPython recognizes these prompts and actually strips them before executing the code. So you can, IPython recognizes these prompts and says, okay, strip those off, and I know where the Python code is in this block of text, and then execute that. And the same goes for what a typical IPython terminal prompt looks like. And then I believe the last bit here is dealing with exceptions. So Python has a lot of information about errors that occur. And when you're doing interactive computing, errors will occur a lot because you're typing and you make mistakes and do things wrong and you're learning and figuring things out. And so good error messages are really important. And dealing with errors and poking around and figuring out what happened is a big part of the process of doing interactive computing. And so here I'm just going to make a file that defines these two functions. And then I'm going to call them. I'm going to import that module. And I'm going to call the function in such a way that it raises an exception. And so this is what exceptions look like by default. In IPython, there's a bit more information than Python shows you by default. But but I can also use a magic called X mode, which changes the how IPython prints errors by default. You can say plain, so that's too much information. X mode plain culls that down a bit to a more sparse bit of information to be a bit more compact. Or you can say, there's a lot of information here. I'm really trying to figure out what's going on. You can enable verbose exception mode. And what this does is when you see the error, in addition to just showing the stack, it's actually showing all the variables and their current values at each stack frame. So if you're having trouble tracking, why did this raise? Why is this one something over 0? What's the value of y and everything? The verbose mode actually shows you at every stack frame, it tells you, in this frame, it tells you, I got the variables f and y, it tells me what f is and what y is. So y is 0 and f is this function. And then in f, you can see that x equals 1. So it actually shows you the value of the locals at each stack frame, which might help you kind of in the debugging process of figuring out why, maybe it makes sense that there was an error with that value, but like, why was it that value? I want to poke around and figure that out. And the default X mode is this kind of intermediate mode that we call context. And we can run additional other shells like Perl and Ruby. So we've got this divide by 0 error, and I want to go debugging. When you ask for input in the notebook, you'll actually get a little prompt to actually input that some response to any prompt. So if we use the debug magic, so I just raised an error, and now I want to do some post-mortem debugging, saying, okay, now let me get an interactive session that lets me poke around those stack frames. So I can do %debug, and you can do debugger commands like BT for backtrace, go down the stack, up the stack, and then say, okay, what's Y there? What's F? Exit. And then we can just ask for input with the Python built-in input function. And that the input function lets you ask the user for input, and then the return is the string that the user typed. And then the last little bit is plotting. So matplotlib is a common plotting library in Python, and we can do some simple plotting. And this gets produced. So we've been dealing with text output up until now, but notebooks can actually have output in a variety of formats in HTML, JavaScript, PNG, etc. And so when you use matplotlib, you get these outputs in an image format, and you get those inline in there. And then a little bit of bonus. So the way execution works in the notebook is that the kernel, so the browser is talking to the notebook server over the web, but the notebook server is actually talking to the kernel over an additional protocol. And the way that protocol works, you can actually have multiple front ends connected to the same kernel at the same time. And so maybe you have this notebook, but you want to switch to a more terminal-like interface. There are a variety of interfaces for Jupyter kernels. There's a terminal interface. There's a Qt console interface that's kind of in between the notebook and the terminal. And the connect info magic tells me kind of what the connection info that I need to connect another front end to this kernel. So there's the connection information dictionary that tells me all the ports I'm using and keys and things, and then there's some handy command line commands that I can execute for how to connect another front end to this kernel. And then there's a magic that actually does basically just does exactly that. This just calls Jupyter Qt console -- existing and then the kernel connection file. And what that does is it opens a tiny text. Opens a Qt console. And this is connected to the same process. So this is just another UI connected to the same process that I can switch back and forth. And so I can say, I've got fig is my figure, and I can see that in this Qt console. And there are some behaviors that can be a bit more convenient to do in a console type interface. You know, I can type and execute a little bit faster and a little bit more efficiently for debugging and poking around in the Qt console than I can or the terminal than I can in the notebook. And so this lets you switch from the notebook where you're producing this nice document over to a more terminal interface where you're doing a little bit more poking around in kind of a scratch area. And that is the gist of the first segment. And we're supposed to have a break at 10:15, and it is now 10:10, which I think is close enough. So if people want to break for 10 minutes or so. Any questions after the first segment? Yeah.
Is there any way to have a interface that is visible in the browser?
Visible. Oh, so the question is there any way to have a TickleTK interface that's visible in the browser? The answer is no. So you can't have TK create things that show up in the browser. But you can, if you're using the local notebook, like I am right now, where the server is actually running on my laptop in addition to the UI, I can run TickleTK, and it will create windows, and those windows will open, and I can interact with them.
Is there any way that I have an application that has a interface on it that I can have somebody remotely access, my TK interface and have it show up on the screen without them trying to install PyCon or Jupyter?
If you want something that for remote, a solution for remote TK, anything that creates real windows via a native actual windowing system, your only answers are kind of actual remote desktop tools. So there are, no machine, virtual desktop, VNC, all these things, or tunneling X windows. So that kind of solution is your only real option for libraries that talk directly to windowing systems. That said, technically you could implement you could implement something that works in the browser, but it would essentially have to be a TK replacement that instead of talking to the windowing system talks to something that generates HTML. Yeah. Yes.
Just open another front end of the same back end.
Yes.
And interacted with them.
Yes.
Is there any kind of auto update on both ends when one updates? Because I did that here and I made some modifications in one. I didn't see the output in the other. I still got same out number listed on both of them. Yet when I look at the history, I start seeing them interweave.
So each cell, the question is about seeing the output from one front end and another one. The console outputs do support that. It's not on by default, but there is a flag when you start the Qt console to say, if another front end produces output, show it to me. There's just a flag when you start up those additional front ends for whether it should, because they do receive that output. And then they make a decision about whether and how to display it. The notebook doesn't display it because the way the notebook is essentially defined is that each one of these executions is an explicit, like, create a cell, put in some code, execute it, and see the result. So we don't want all the executions in another environment to add a bunch of cells to this document. That's part of the reason that we actually switched to that other environment in this case, was we wanted to do some poking around without creating cells that we're not interested in. It's the information is available and it's technically possible. It would be possible to say when I run code in another front end to create a cell here, that information is available and we could do it. We just choose not to, essentially. There was, yeah.
So, at the top of this notebook, every output is preceded by an output history number, and then somewhere along the line, they stopped doing that and came back to
So the out, this is something in Python called the display hook. So cells can have output. So this is a print statement that wrote to standard out. But if I just do 1, so this, if the last, be careful about terminology or I'm going to get it wrong. If the last statement in the cell is an expression with a value that's not none, then IPython will automatically display that and store it as the result of the cell. So you only see this out if the cell has a result. So since print returns none, there's no result, so we don't save it and you don't get an out prompt. But since 1 has a value, we save it and store it. Yes?
Could you give an example of spinning up interactive terminal connected to this cell? So for example,
A terminal, not a Qt console?
no, just regular IPython.
So it's not regular IPython, but it is in a terminal. What was it? That's wrong. Yeah, and then there's this. So this is Jupyter app, and then -- existing, and you don't really need. Yeah. Yep. Yeah. Yeah, it's connected to the same. That is just if I. Yeah, it shouldn't be 1. It just hasn't asked what the number should be yet. So I can do fig, which opens up in a window in this case. Yeah, now it's actually 10:15, officially break time.
should we restart? Is everybody there? Still a couple of people missing. Well, just I'm going to make an announcement before we restart. We have JupyterCon in August in New York City. So if you like Jupyter and you want to attend awesome talks, you can go to jupytercon.org. It will redirect you there. And we have stickers and cards if you want to get all the information for later to stick on your laptop and everything. And feel free to spread the word that we're looking for attendees and we have awesome speakers. It will be the first time we get a Jupyter conference, and it works great. We will try to get one every year. Okay, so let's continue for the second part of the tutorial. Okay, so Min ended his presentation at the perfect time. Let's restart slowly to get you back into your computer. What we saw there was mostly features of the Python kernel, and Jupyter has a relatively clear distinction between the front ends and the kernels. And you saw just at the end that you can have many front ends for the same kernels, and front ends may have some slightly different features. So, for example, when you're using the IPython kernel, you might get different things depending on whether you're using it from the notebook and the terminal. So I'm just going to show here two small differences between the front ends. So here I have a notebook, and I'm going to import NumPy. And if I want to get some information, for example, on numpy.histogram, so I can complete. And if you open a bracket and press Shift-Tab, it will give you directly inline some information about histogram and how to use it. If you are writing a really big function and you don't want to do numpy.histogram and then question mark to get information at the bottom, it can be quite useful. And this tooltip is something which is specific to the front end, to the notebook front end, which you don't have, for example, in the IPython terminal. Though you have things in the IPython terminal that you don't have in the front end, at least not yet. So, for example, if you create a new terminal, I'm going to zoom in a bit and start IPython. You will see that since one of the latest versions now, you have code highlighting in the terminal as you type. So you can define Fibonacci function that takes input n, and if n is lower than 2, then return 1, else, oops, return fib on s minus 1 plus fib of n minus 2. So first, what we will see here is that in the terminal, we also have multi-line input. So we can go up and down, which most REPL don't give you. That's because we're using something called prompt toolkit. And what you can do is add new line in the middle with Control O if you don't know that. But the fact that we're using prompt toolkit allows us to do some really advanced completion. And so, for example, if I import NumPy and I do numpy.histogram, you see that now at the bottom of the completer, it will tell me the type. Here it can't infer it, but it will tell me the type of the object it's completing to. That's something which is not yet in the notebook, and which can be really useful. And that's currently on the stable version of IPython. And just to give you a small sneak peek, because you're here, on the latest version of IPython, if you try to complete, it will even tell you the signature of your function while you're completing. So you have features like that are core to the kernel of the language you're using. So the magic, the bang to execute shell command is specific to the Python kernel. And you have other features like tooltip and some UI completion that are specific to the front end. And that's sometimes confusing when you're changing languages, and that's what you're going to see now, is how to use many languages with Jupyter. So if we go back to IPython in depth, I have things that are already running, and you can find in example IPython kernel that IPython supports rich outputs. So let's go there. And so one of the features that the notebook frontend supports is for objects to display themselves not only as strings, like in the terminal, but as images, as math, as sounds, or any other MIME types that you want. So if you're writing a library and you want your object to be displayed in a different way, you can define specific methods on these objects that allow you to display images. So IPython provides a function which is the equivalent to print, but we call display. And display will allow objects to show better representation, richer representations than just strings. And it's situated in IPython display. So usually when you want to start working with IPython, you want to import that from IPython itself. We don't inject it by default in IPython, because if you want a notebook and you export it as a Python module, we want everything to be, we don't want people to be confused. Like display wouldn't be defined if you run an IPython script with pure Python. So here we are explicit, we're saying, oh, we run in IPython, we're importing that. It wouldn't work if you were in a pure Python REPL. And we have other convenience methods that allow you to filter the representation an object gives. So if an object is able to show itself as PNG, as LaTeX, as SVG, as JSON, you want to be able to say, show me only this specific representation. And these are also in IPython display. And so, for example, if you want to show an image, we provide also a convenience class called image. And so, for example, what I can do is I can load an image, assign it to a variable, and now when I return this object, when this object is the last statement of or expression of a cell, it will be assigned to the output number 5. And there is a slight difference between returning the last object of a cell and displaying this object. So here I display I, and you see that both are almost identical, except here I have out number 5. So if I try to access out number 5, like you saw previously, I would get this image, I would get this rich object, while out 6 would be none. And this is the same difference in the Python REPL when you print a variable and when the variable is the last value of a cell. And you have various options. You can show things from URL. So if the Wi-Fi conference was down, I would have an image not found here. And you can also display SVG. So here I have an SVG. So depending on the kind of representation you have, if you want something that is scalable and is simple, you might want to use SVG. We have a couple of convenient things, like when you have an image, do you embed the data of the image into the notebook? Or do you just soft link to the image by saying this is the URL of the image? So for example, here, I'm not going to execute. This was the Lawrence Berkeley Hall of Science last time I ran this notebook. When I ran the cell above here, the data was embedded into the notebook. And in the next cell, when I say something equal true, this is actually currently pulling from the live feed. So if I were to refresh the notebook in 10 minutes, this image would change, and this image would not. Of course, if you want to target reproducibility, you might want to embed your things. You can do the same. Actually, let me make that more compact. with a lot of different convenience methods. So for example, if you want to display HTML in a notebook because you want something to be well represented, you can use the HTML object, which is again in IPython display. And now you create the object and you can say display H. And if you've been using pandas to show data frames, that's what pandas is using. And so your data frame will be represented as nice HTML. And even when you hover with your mouse on your row of your table, they will be highlighted so you can easily see what's happening. If you're just trying to throw some HTML on the page, one thing you can want to do is use the HTML magic. So here we see it's %HTML. It's available by default in the namespace, and you can see here it's the CellMagic. It doesn't take any arguments on the first line, and you can write HTML, and again you will have HTML here. You have a lot of convenience method. Here you can also display JavaScript, and here I'm going to execute this. That will display. Oops. That will display some JavaScript that will run on the page, and so now we have my page that say hi. There are some security concern about executing JavaScript on the page, and you will see here on the top of my screen, it says that my notebook is not trusted, which means that I was not the person who produced this notebook, which means that outputs that are insecure won't be shown by default. That's one of the things where when you're sharing a notebook with someone, you can get a difference. You might see something on your page, and they might not, because they might not have executed the notebook. So you have two ways of trusting a notebook and getting all the rich outputs that can be, for example, dynamic graphs that you can manipulate and do brush selection. Either you click on not trusted and say, well, yes, I trust the person who made this notebook. This notebook is not going to destroy my computer. This notebook is not going to steal my credential, and so on and so forth. And you click trust, and the notebook will be trusted and reloaded on the page, and then untrusted output will be shown. Untrusted output is everything which is HTML, JavaScript, and may execute code on the page. Or the other possibility is to go to cell all output clear, so it will remove all outputs, and then you want to run all cells. If you run yourself all cells of a notebook, you're executing all the code, and then the notebook will be automatically trusted as being yours. If you're working on multiple machines, what may happen is that it will be trusted only on some machines. There are ways to synchronize that, but that detail. So keep in mind that if you share a notebook with someone and you have a difference in appearance when you load the notebook, it might be a question of trust. And look at this symbol. We're just going to skim through the different things you can do. You can display. Oops. Some complex JavaScript. Keep in mind that if you display JavaScript or HTML, it might not work on all front ends. So here is something that will be specific to the front end that allow you to display JavaScript. You can have nice math if you're doing applied math or any thing where you need equations like electromagnetism. You can display them as actually nice LaTeX. And we even provide, if you're writing Python 3, if you actually want to write math with Unicode symbols, you can do theta tab, and it will give you a theta and then dot, and I will have a theta dot that I can assign to, I don't know, 13 radians, and it will just works. That works only on Python 3, but it's quite useful when you want to have compact equations. So you can display LaTeX and you can display audio. If you've seen recently, some gravitational waves were measured by the LIGO interferometer. And one of the things they did is to actually release a notebook that does the analysis. And at the end of this notebook, they produce 2 audio files that are actually frequency shifted version of the gravitational wave. So you can literally listen to the 2 black holes that are colliding. So you can have audio.
Thank you for installing Express Dictate. You will find Express
So
Dictate.
I can directly have audio in my notebook, which might be useful if you're an ecologist and are studying birds or different kind of animals. So that's just a quick overview of how you can display in a notebook, of course, by videos and a lot of other stuff. And you might want to define your own representation. So example, IPython kernel. So if you go to example, IPython kernel and custom display logic, you can see how to define your own objects that can have rich representation. The things to keep in mind is that when you define certain objects that, for example, define LaTeX and PNG and text, when you display the object, everything is sent to the browser and only one is shown. But when you save it, all the three are saved into the document, which means that if you convert after the fact to, for example, PDF, the PDF exporter might want to extract a different representation from your object and show it differently. So, for example, if you have if you're working in neuroscience and you're showing a brain in the notebook, on the live notebook in HTML, it might be a 3D model that is represented. You save it, but when you export to PDF, the PDF exporter might say, well, I am actually going to display not a 3D model, but slices, because of course on my PDF, when I print it, I can't rotate my brain. So I want to have the multiple slices. So the way to do that, let's import again display and matplotlib, is to define specific methods on your object that are underscore wrapper underscore a name, which varies, which tells IPython what is the kind of representation I want for my object. So for example, pandas data frame will do an HTML and I think a LaTeX one. And when you will display this object, IPython will see that it's there, call it, get the data out, send the data to the front end, and the front end will display that. So for example, let's say I'm working on probabilities, and I'm creating a Gaussian object. What I can do is I use a specific method to pre-compute a graph, and I also want to have, for a PNG, and I also want to have a LaTeX representation, which is my Gaussian is just this mean and this standard deviation, because when I render to PDF, I don't want the whole image. So I have my Gaussian object, and what I can say is create a Gaussian object with mean mu is 2 and standard deviation sigma equals 1. And what you can see is that it will automatically, when you return it from a cell, it will automatically show the right description. So the front end has a preference of what it thinks the best representation is, but you can tweak that and say, well, I actually would prefer to have PNG first or prefer to have SVG first. And of course, you can also call the display on this object, and it will show on the screen without the out number here. And same object, I'm not recomputing anything. I'm just going to ask IPython filter and keep only the PNG data. And I get the PNG data for my Gaussian. So you can explore the different representation of an object without having to recompute all that. The only drawback here when I'm calling display PNG is that it will actually strip all the other representation, which means that now here in the document, I only have the PNG data of this object. So if I convert to PDF, here the PDF would have to embed the PNG because the math and the LaTeX is gone. And so you can try to change the number of sample, and you can display two Gaussian next to each other. And if you're developing a library that does a lot of that you're using a lot, and you want to have nice representation, if you're always using the same thing, you might want to create this representation for your object. So, for example, let's say you're working with NumPy polynomials. I personally have issue reading that. You know that it's the value for each power of x. And you can say, well, actually, I want to represent my polynomial this way. So how to convert a NumPy polynomial to a LaTeX representation? So you see that if you call it on the polynomial, it spit out nice LaTeX that is not yet represented. And now I can just pass that to the LaTeX function. And now I will have my nicely represented polynomial. And what you can tell PyPython after is, well, I don't have access to NumPy. I don't want to change the source code of NumPy. But I, as a person, prefer to show this object in this way. And you can tell it, how can I tell you the way to represent objects? And so here you see that IPython knows how to display some built-in object, either as SVG, JavaScript, plaintext, JSON, etc., etc. And you can teach these things how to display each object. And you can here get the LaTeX formatter and say, you can look at the help, which tell you exactly what are the different signature, and then you can say, hey, IPython, here is how to represent NumPy polynomials. And now suddenly my polynomial that was showing up at strings before has a nice LaTeX representation and makes it much easier to read and to go through your day when doing data science. If you really have some complex objects that need to do several steps, things like fetching JavaScript to get libraries and sending data, you can completely customize how IPython is displaying objects by using a rich thing called IPython display that we will not see right now, but for example, we won't play with it, but you can use a JavaScript like D3 to display a plot. Here it's neither SVG nor PNG, it's something called float. And so this is part of the Jupyter protocol. Like an object can, in the Jupyter protocol, send something across the wire. And so if you develop a kernel for Jupyter, regardless of your language, you can make use of this. And you can have R, you can have Julia, you can have Haskell to display rich objects. The exact implementation on the kernel side will depend on the language. Like Julia does not like to define a method on objects. They have a registry on how to display object, and you don't define then the wrapper method like we do in IPython. In Haskell, it's again different. And now what you're going to see is how to install multiple kernels for Jupyter. So let's go back here. Let's go to example notebook, multiple language, and front ends. So when you're working with Jupyter, you might want to work either with different languages, or even when you're just using Python, you might want to work with different environments. In some environment can be in Python 3, some other in Python 2. You might want to have several versions of a library in different environments, and you don't want all of that to conflict. You might even want to have a specific process that runs on different machines. So for example, you might collect a lot of data, and you don't want to move your data around in your lab. So you might want your Python kernel to actually start in your experiment room, or you might want to work on a specific beamline if you're on a synchrotron. And kernels are basically that kind of things. They are not always one language. They are one way of starting a computation process. And this process may be one language, it may be many languages. And that's how the Jupyter protocol really help, because then you can just defer to anything that implements the protocol is a kernel. And the kernel can be whatever you want. It can do whatever. It can be a chatbot. It can be anything. So at the base, IPython is a REPL. So basically, you have a while loop. You get code from the users by using input, and you figure out some way of executing the code and sending that back to the user. That's roughly it. After it's just cherry on top. You just make things prettier. And what we did is abstract that into the network protocol, which is now the Jupyter protocol. And so you have the core execution, which knows how to get information from the user, execute it, and send something back. And then you can choose, how do I get this information and send this information back to the user? And so terminal IPython, when you're in the terminal and just type IPython and get the shell prompt, is basically saying, I'm going to hook into my core execution engine, but I'm going to plug into it via standard in and standard out. And what we did is basically say, well, actually, we don't want standard in and standard out. We're going to switch to a network protocol, and we're using 0MQ. 0MQ is relatively widely available in many languages, relatively easy to build on. So if your language have 0MQ binding, there are a couple of methods you can implement on and respect the protocol, and then suddenly you will get a kernel for your language or your project that speaks the Jupyter protocol, and you can directly make use of all the front end. You have different ways of going of implementing a kernel. Either you're saying, I'm going to implement my kernel for my language in the language itself. So that's what we did for IPython. IPython is in Python. But you may want to say, actually, it's a bit complicated in R to write ZMQ bindings because R doesn't have good packages. But I know that R has really good Java bindings. And so recently we got some people who said, well, we wrote an R kernel in Java. And so there was already Java bindings for 0MQ and nice Java binding for R. And so now there is a R kernel which is in Java. There is also an R kernel which is not native R. But you can decide to go different routes. And so when the language that you're executing is not the language you use to write the kernel, we call that wrapper kernels, and you also have native kernel. And so the way it works is you have your users, you're smiling because it's PyCon and you like that. And you have your browser, and your browser is actually speaking through WebSocket, through the network to the notebook server, which holds all the notebook documents and has access to your file system. And your kernel is even remote from your notebook server, which means that you can not only have your servers that store your document in one place, but you can have even your kernels that are remote. So you can even more distribute execution. And each kernel may even talk to a cluster, which is a different machine. So each of these boxes can be on a different machine. So if you have a lab and you have heavy computation, you can actually really distribute all that. It might be a bit complicated in some cases, like when you're running everything on your laptop, the path to your different files is relative to the notebook server, and the path of the file that you see when you're executing code in the kernel is depend on where your kernel is on the process is on your file system. We had the confusion earlier, like when I write logs files to disk, why aren't they next to where I started my notebook server? When your kernels are on different machines, you can see a completely different file system. And it's something that you might want to keep in mind. And so now the question is, I have my Jupyter with my Python 2 or Python 3 kernel right now. You can see which kernel you have by going to the kernel, change kernel, and see which kernel you have here. You probably only have one. And the question is, how do I get more? So what we're going to do is install more languages. So if you're using Conda or Python, you probably have already Python installed. You might say, well, I want to create a new kernel and register it with Jupyter. So the way to do that is in Python, you create a new environment. You get into this environment. You install the kernel into this environment. And then you register the kernel with Jupyter. So here are the instructions I'm going to do it live and create a kernel named PyCon. So here I already have Julia R, Python 2 and 3. I'm going to go there to do new terminal. So I have a new terminal. You need to do Conda, create. You can use virtual env if you don't have Conda. I'm going to give it a name. PyCon 2017, and I want Python 3.4. So it's going to create the Python 3.4 environment. You can do it at the same time and even try variation if you want. So let's say yes. And so in the environment, I don't need to install all of Jupyter. I just need to install the kernel. It's a bit slow. I shouldn't have done Python 3.4. The Python 3.6 would have been cached. I just need to install for Python, I need to install IPyKernel. So what you can do is source activate the environment, and in the environment you install IPyKernel. You just need IPyKernel and all the library you need. Let's put that just next to. I'm going to give here's the instruction. So what I will do after, I will install IPyKernel, and then I'm going to ask IPyKernel to install itself and give it a name. The name, you can give it both a name which is machine readable if you want something which is only lowercase ASCII for machine consumption purpose, and you can also give it a user-friendly name, which is, I don't know, temporary, whatever, because I'm going to try new libraries, or you want to have a stable environment and a dev environment. So let me retry with Python 3.6. And so once you register your kernel, it will drop a specific file on your file system that tells all of the Jupyter ecosystem, here is how to access my kernel. While it's doing that, I can show you how to do it with the R kernel as well. So if you have Conda, you might want to install R from the R channel. Oops. Here. So -cr is saying, look into the R channel, install R. I also want to install the R IR kernel. And with R, the way to install is slightly different. You need to start an R session and say IR kernel install spec. And what this will do is actually drop a file again on the file system that will give me access to R. And then the R kernel should just appear here in your menu if you refresh the page. If you're not using Conda, you might have to compile things on your own. If you use install packages, these things, and then devtool install GitHub IR kernel, it will download things, compile things automatically. And once this is done, you can go back here and redo IR kernel install spec, and it will do the same, install the specification, the kernel spec on the right directory. If you are at the command line, you can also see where all of your kernels are installed. You can issue a Jupyter kernel spec lists, and it will tell you where your available kernels are. And you can see here that I have a Python 2 kernel, which is my system one, which is in user local. I have Python 3 and Julia that are actually installed via Conda. And you have this one, which is is per user. So what you can have is have your system admin install kernels that are global to all users, and all users have access to them. And if you want to have a specific version, which is just for you because you're messing around with some libraries, you can install in your home directory. And then your Jupyter notebook can switch between each of those. And so now I can do source activate PyCon. Conda install IPy. I don't know how to type. So sometimes installing doesn't always work because it can take quite a long time to compile. I've deployed a couple of 1 hour ago. If you go to this IP, there is a server which have you can put any username and login, and it's already have R, Julia, Python 2, and Python 3 installed. And you can play with it if you are not able to install it on your machine. So you just put whatever you want and smash the keyboard. Probably not using semicolon. And put whatever you want as a password and sign in. And after a minute or so, you should get a server that have all the tutorial material and Python 2, Python 3, R, and Julia available. This is temporary. It will stay up only for the day. But you can play with it. And that's what we're going to learn how to deploy in the third section. OK, so it's installed at the same time. And now I can do Python -m IPy kernel install -- I give it a name, my super PyCon kernel. Good, permission denied, -- user. It's installed. I go back to my notebook. I'm going to refresh the page. And hopefully, if everything is right, I now have my super PyCon kernel, so I can switch to it. And it could be a different language. If you have been doing it with R, you should have an R kernel available. If you did it with Julia, you can have a Julia kernel available. And now I can just, either when I create a new notebook, I can select my language directly, and it will create a notebook with this language. Or I can actually switch the language of a current notebook. It's going to kill the current kernel and restart a new one with the spec you've selected. And so here now, I'm not an R person. I'm sorry. You can actually run R, and it just works as long as it implements the protocol. You can even get nice inline plots. So that's the first step. And the next step we're going to see is one of the requests we have is, well, a notebook is one language. I actually want to have many kernels per notebook. How can I do that? And it's often the wrong question, because the kernel is a thing that allows you to execute code. A specific kernel may not be a single language. And one demo you have here is that you're actually using a Python kernel to run both Python and Julia. The way we do that with the IPython kernel is to say, well, we're going to tell the IPython kernel when we want to switch language by using magic, because the magic doesn't have to be Python syntax. So what we're going to do is load julia.magic, which is provided by the Python Julia package. And what this does is it injects %% Julia and % Julia in the namespace. So we can use CellMagic for Julia and LineMagic for Julia. The CellMagic for Julia allows us to execute code in a Julia process. And the LineMagic allows us to send things back and forth between Julia and Python. So here the Python process and the Julia process are persisted, not some like other magics. Other magic are just starting a process, running some code, getting the result back, and killing the process. Here you have two live processes that are talking to each other and doing things. And so what you can do here is say, hey, Julia, import matplotlib from Python and import numpy from Python. Oops. It takes some time because it starts the Julia interpreter and does some magic under the hood that I don't understand. And then you can say, Julia, use what I just told you to import from Python to draw some stuff. And so you see here, I have linspace. Linspace is definitively not something we know in Python. It's not in the normal namespace. So it's Julia. Pi is also Julia. T we just defined before, it's Julia. Sine is Julia. NP cos is numpy, so we are using a numpy cosine. T is Julia. PLT comes from Python, it's matplotlib. Get current figure. And let's plot TS in red with a line width with -- and a label. So that's just Julia. And after a few seconds, I get a nice figure. And so here I use the Python process to talk to Julia and got things back. And now I'm thinking, well, but I don't like to interact with matplotlib via Julia because I don't know all Julia syntax really well. I'm going to pull the figure back from Julia into Python and modify it. So you can use %Julia to send things back and forth. So you can say, well, Julia fig, assign it to fig. So this thing is Julia. The rest around is Python. And what you can do is, plot a sign on top of it. I was not really inspired when I did that. And so now you have these cross-language things. You have in the same process, you have Python and Julia just using Magic. And just to be a little bit crazier, because this is just sending data back and forth, we're going to define Fibonacci. If you remember Fibonacci, you have Fibonacci of n, which is Fibonacci of n-1 plus Fibonacci of n-2. Either you recurse implicitly, or you're crazy and you're passing the function you want to recurse with into Fibonacci. And we're going to write Fibonacci in Julia that recurs using the Python function, and the Python Fibonacci function that recurs using the Julia Fibonacci function, just to see if it works. It will probably not, but let's try. So you can see that in this cell, I define pretty tersely Fibonacci in Julia that recurs using pyfib. And I define Fibonacci in Python that recurs using fib, and fib will be Julia fib. And I'm just going to not execute it, just to for the thrill. So it compiled, and can I run it? Yay, it works. What I can even do is print P every time I move from Python to Julia, and J every time I go from Julia to Python, to see the interleave stack trace. And I have Python, Julia, Julia, Python, Python, Julia, Python. So you can do some pretty neat cross-language things in the notebook if you wish to. It seems really magical, but it's not that hard, and that's what we're going to see how to do that. By writing a custom magic. So let's go to exercise, sorry. Exercise, customization, custom magic and cross-language integration. So a quick reminder, magic are an escape hatch that allow you to inject whatever syntax you want in your IPython process. You have line magics that are %magic and get a single string, and % magic that get both the string that are after it and everything which is below it. And we're going to define a simple TikTok magic just to get our hand dirty. I give you some hints on how to start. You need to import something from the core of IPython to teach IPython that some functions are magic. So you will need register line magic from IPython core magic and register line CellMagic. Register line CellMagic is telling IPython that a magic can be both a line magic and a CellMagic. And we're going to import inspect to inspect some stuff. We can look at documentation for register line magic and say, well, use it as a decorator without argument. You can, or with argument also if you want. And you define a function underneath, and you can read the rest, and it tells you that it will actually take the function and register it with IPython. We will also inspect compile, because you might want to compile some source code and probably execute it. And try to see if we can make a TikTok magic. So what we were going to try is not look at the solution, but do something like register line magic and def TikTok. It's a magic, so it's a line magic. So it's going to take a single argument, which is a string. So it's the string the user wants to execute. You don't have to call it that long. You want to get current time. Execute user code. And get new current time, do the difference, and return the difference. I will give you a few minutes to try to do that on your own and see if you can get TikTok magic. If you want the solution, it's just below it. Just uncomment and run that, and it will give you the solution. I'm going to try to do it at the same time. So let's see. Seconds. Microseconds is maybe too much. Seconds. Oh no, that's 2 microseconds. Okay, so let's do that. Probably you want to do a string. So I'm using Shift Tab to see the signature, and it's the source. So it's a string, and it's a file name. At PyCon. Then we want a mode. We're going to go with exec, and then we're going to exec that in. That won't work. Let's do nothing. It will be a basic magic, but it should work. And let's go with after. Before. Now. After. Return after minus before. We have now TikTok. We have TikTok here, and let's do 1 + 1, 54 microseconds. We can compare that with % time it 1 + 1. That is way more fancier than what we did in 5 minutes. Well, there is some overhead. But you get the idea. Let's check my solution. And I did total second. Well, different way of doing it. Okay, and I was typing things. Name error. PyFib is not defined. Ooh. Oh, yeah. In my version I live coded, I didn't pass globals, so it couldn't get access to functions defining the global namespace. You just need to look at Python documentation to know that. But you see that defining a magic for yourself, if you have something which is that you already often do and calling functions are difficult, you can just pretty easily do that in the fly. And because your magic is now returning something, what you can do is use it in the middle of Python code, and you might want to look at your Fibonacci that I defined here, which is a bit ugly. It's using the dummy recursive algorithm, and see how long it takes to run. It's going to give me some results. I give you some functions to plot it. And you can see that, so this is a semi-log plot, and you see that there is a nice straight line that appears here, and it's pretty slow. Of course, I'm not doing the right algorithm, but it's pretty slow, and I might want to speed things up. And often when you're doing scientific computing or anything else, you want to have just a chunk of code which is really fast. A little short on time, so we might skip that. The TimeMagic, you can look at basically how TimeMagic is using different options. So what you can do is do time it and do 2 question mark. It will show you the source, and you can see how TimeMagic is doing most of, so that's a doc string, most of the work. Toggle header and toggle toolbar. And so you can see that the TimeMagic is way more complex. It's actually a class. It has a lot of moving parts. It can access the namespace, inject things in the namespace. But you don't need to go all that fancy unless you have some really complex things. And so we want to go faster because our Fibonacci is too slow. So we're going to say, well, I want to embed C in my Python. And I really don't like most of the libraries that are around because, as Min said earlier, it needs a lot of boilerplate. And if you're working with people that don't like boilerplate or just want to get work done, you might want to just write a magic. So I give you basically how to write a Fibonacci function in C. If you squint closely, you see that there is a big mistake. But let's not fix it now. We have the header and the source, and if you go online and you say, well, how can I compile C on the fly in my Python process and get a shared object which is fast, tells you, well, you probably want to use CFFI. CFFI is nice. It's not too hard. It's only 20 lines if you want to write a function. So let's import CFFI. Oh, it's not there. We're in IPython, so what we can do is add a cell above. And we want to install CFFI for the current Python. And so we're going to use a bit what we've seen earlier. We're going to use sys.executable, which will be the path to the current Python, -m pip install CFFI. And it's installing CFFI. It should. Oops, it's fast. And now we can re-import things, and it works. And you can look at the CFFI documentation. I give you most of the things here. You will need a file name because CFFI will compile things into file name.sharedObject. You need to create an FFI context, set the header of the function you want to compile, set the source of the function you want to compile with the file name. Then you ask CFFI to compile this object. It gives you a shared object, and then you want to import this shared object because it's dynamic. You want to use dunder import or import lib. I'm going for dunder import, and then you want to inspect this object and see that it has something called cfib, because if you look at the source above, it was cfib. Oops, I'm here, and you want then to get the cfib object from the module.lib.cfib thing, and you can look at this documentation, and it's your function. So now, hopefully, you've assigned cfib to this, and you want to measure it, and it should be way faster. And that's just showing you how to do that. So that's the orange stuff, and you see that it's at n equal 20, it's way faster. It's still not right because it's a dummy algorithm. But you just gain 2 or 3 orders of magnitude in speed. But that's still a lot of boilerplate. So what you can do is write a magic class with some information here. Can you make something which is %% that take your C function body and compile the function you wrote there and inject it into the namespace. And that's the exercise we have just after. I give you the basic template of how to do that. Here we are using a class because when we instantiate the class, we give the class access to self.shell, which is the current IPython session, which means that now you can poke around the user namespace, and you can look at what are the things the user has defined, and even define things for the user. So for example, if you do that, you can do user ns, which is a user namespace, and assign to the variable fib the function that does nothing. I'm going to let you do that. And one thing to know is that you can't reload a shared object in Python. So what you might want to do is compile it with a random name, import its random name, so that it is different every time you redefine, you rerun the magic, so that you can basically have interactive C. You basically do %%C, you define your function, and if your function is wrong, you fix it, you rerun it, and your function object in your namespace have changed. And so you can, I will give you 5 minutes to try to get some of that. If you really don't want to do it, what you can do is pip install CFFIMagic and poke at the source. Something like import CFFIMagic and see, oops. Actually, it's already there. And you can get some hints of how to do it. Okay. 3 minutes, it's not a lot, but we have a third section. So you just take what's above, you can just copy and paste it, and you see that it should technically just work. And otherwise, you can poke around in here. You can see that I have my random name, that I have my FFI contexts. I set the header, I set the source with my random name. I compile. I import my module, and I will just loop around the attribute of the thing I just compile and set the user namespace to set the value in the user namespace to the function in the module name. And now it's registered, and I have my function. And what I want to do now is look at cfib I and pyfib I for I in range 10. Let's see, well, is my C correct? Ooh, Invalid syntax, I forgot parentheses. And you see, ooh, that's strange. My C function and my Python function should have the same value, right? Well, I forgot here, it's not 4, it's 2. It was pretty obvious. It might have been more sneaky to do something like that, where it's just a single equal. But the thing is, you can redefine your C function. You can just do that, and now you have a C Python extension that just has been recompiled under the hood and re-imported in your global namespace. And now your value are correct. And this function is 2 or 3 order of magnitude faster than the Python function. And so if you want to go much faster, you can now just using that iterate over your problem way faster without having to go through a lot of boilerplates. And you have nice syntax highlighting, which you don't have if you use a Python string. And we can compare the speed, and we see that probably, yeah, the C function is blue now, and you see that it's about 2 order of magnitude faster than my Python function. Just a side note that, of course, the implementation is a dummy algorithm, and if you improve your algorithm, you can get way faster. Actually, it's not C, it's Python now. New algorithm. You can see that Python can be way, way, way faster than C if you use the right algorithm. Of course, you can use the right algorithm in C and then be again way faster than Python again. But choose your battle. It might be easier to write a more complex algorithm in Python because it will be shorter than to get it right in C. So you have to trade flexibility and speed of writing for speed of language execution. And so all of that was running from my laptop. So you see that here I have a C function, and I could also use a JuliaMagic, which means that in a single notebook I could use Julia C. I can use RPyToMagic, which allow you to have R in the same process. And you can then, in your single notebook, with a single kernel, you could write something in 5, 6 different languages. There are magics available for Python, for Fortran, for Rust, for C, C++, I don't know, for Julia. And so all of that should, if you manage to install it, which is not always easy, should just work after easily. And the way to develop it would be to often use Docker container, and you might want to deploy that on the cloud. And that would be our third speaker, who will take place here. I don't know if we have a break again or not. So I'm going to leave the stage, and we're going to deploy things on Google Cloud. Thank you. And come to JupyterCon. Yes.
So, part you had about installing a new kernel that you did it yesterday, which I realized I hadn't told. What's your workflow when you're working on a Jupyter notebook with people, and say you push a change like that, and I've got a little time where I've already made changes, stats. Does that work well with a big workflow?
So you have ways of doing that. You might want to install Git clean and smudge filters. I don't have them installed right now, but Git clean and smudge filters are basically operation you do on the notebook when you commit them from your working directory to your index, and back when they go from your index to your working directory. So for example, what you could say is, when I commit this notebook to my repository, remove all outputs. And so the committed version wouldn't have any outputs. So that's a simple way. But for example, what some people are using, what you can do is actually explode a notebook to separate multiple subfolder, or convert a notebook to Markdown. So when you commit the notebook, so the notebook is actually committed as Markdown. And when you check out the notebook, it goes back from Markdown to IPython. And under the hood, you just don't see it happening. For you, it appears like it's a notebook, but then for the version control system, it's going to be Markdown. Notebooks are in general challenging for versioning system, and Min is working on NBDime, which is diff and merge. Let me do NBDime. Network is not NBDime. So dime is for diff merge. And so basically, it gives extra hooks. So basically, if you have conflict, you will get with this UI, which understand the notebook format. You need to configure Git to do the right thing, but all the instructions are here. And then you can choose, like, here is the figure before, here is the figure after, which one do you want? And then you can resolve your merge conflict in a graphical way. Of course, GitHub does not understand that, and you need to resolve the merge conflict locally, but anyway, you always need to resolve the merge conflict locally. You might just have more merge conflict. Does that answer your question? So we're also working on real-time collaboration. And if you've heard about SageMath Cloud, it's something that hosts Jupyter. It's not the only thing. But they have real-time collaboration. They don't support all the features of Jupyter yet. But if you're not working with Git and you want to be several people on the same notebook at the same time, that will handle multi-cursors, multi-people you can chat on the page. And we are working, Jan is working at Berkeley. He's not here today. And he's working on integrating Google Drive with a normal notebook frontend. So you could, hopefully in a year, something like that, you have your local install of Jupyter, and you say, well, I want to collaborate actually right now with someone. Click the share button. Say, well, Min, can you help me on this notebook? And Min get an invitation, and then I can see Min doing change on my notebook. There are some complications, like when you have real-time collaboration, who owns the kernel and what is the execution model is obviously questions that we're pondering, because if I'm sharing something with you, and I execute something. Do I execute something on my computer and you execute on yours, in which case both kernel get out of sync because you can't share live interpreter. But one thing you don't want is that when I press Shift-Enter, you don't want me to execute code on your computer, of course. And that's the challenging part of collaboration also on Notebook, is that you have not only the document has a static state, but the document is often coupled with a dynamic state, which is the state of the kernel. And that's why merging notebook don't always make sense. So if you take a notebook like this one, if you go to this URL, this notebook, exactly, because there is no password right now, and we both collaborate on that, it's like having two open windows of Emacs and each of us pressing save. They will clobber each other. They will share the same kernel, so if I execute a equal a plus 1 and you execute a equal a plus 1, then it will be a equal a plus 2. But that's not, you should not collaborate using a single notebook server. You should go a layer above that we're going to see with Jupyter Hub, and real-time collaboration is not something which is ready yet, unless you use a service which already implements it. And each user has their own server, and they should be authenticated to their own server because their server runs as them. You don't want to have someone else access to your server. And so that's why, if you look at, let me log out. There is a huge warning, set up HTTPS and set up a password, because even on your own machine, you're exposing a network port, and someone who is not you may send requests to your server if your server doesn't have a password in HTTPS. Yes. It's, technically you cannot do it, but that's how the current notebook frontend works. So if you spawn 2 servers on the same local directory and you open the same notebook, they will have different kernels, it will be different server process, they will write to the same file. It's like opening 2 Emacs windows or 1 Emacs windows and 1 Vim windows and 1 Sublime windows. Technically, the notebook content manager may not be a file system, it may be a database, so it may be whatever you want, but that's hypothetical. Mathematica. So if you're doing, I mean, that's not directly related to Jupyter because we are basically just allowing, the question is how to migrate from Mathematica to something like that. We don't have a nice story for that because people can use whatever libraries they want underneath the hood. We're just basically prettier on top. If you're doing symbolic math, you might want to look at SymPy. But after, it's a question of what are you doing with Mathematica? Because Mathematica tend to bundle everything. The question will be like, what are the libraries that are useful for your use case? If you're doing statistics, you might want to look at Seaborn. If you're doing brain stuff, you might want to look at MNE. And that will depend on your specific use case. And all of these libraries in Python and in Julia, if you're using Julia, should work with Jupyter. But it's a case-by-case basis. It will depend on your language. In Python, more and more the scientific community goes toward Anaconda. Anaconda is a lot of things that are together. But then after you might have, for example, if you're dealing with image, that's why you have scikit-image and that's why you have scikit-learn. They are basically, hey, let's get all of the things together that are dealing with machine learning. Let's get all the things together that are dealing with images. MNE is the same thing. It's let's get together everything which deals with brains. For Python, for Julia, I don't know enough, but they have similar things. They have Julia opt. If you're doing optimization, you want to look at Julia opt and go to the Julia opt organization and download their stuff.
Okay. Okay, so as Matthias mentioned, we'll be looking at Jupyter Hub and how to deploy that in Google Cloud. So as you're probably aware, so far obviously we've been looking at the Jupyter project, which itself is a server where you can launch multiple notebooks. That's essentially a single user environment, modulo the discussions we've just had. But with Jupyter Hub, it's something where you will actually have completely separate Jupyter servers isolated from each other. So something you would typically use in a classroom setting where everyone will have their own environment. So just to show that in a pictorial way, we have Jupyter Hub, which is using Docker Swarm to create a group of Jupyter notebook servers, which are all isolated from each other. Okay. The Jupyter Hub work is funded by the Berkeley Data Science Education Program, just for information. And what I'm going to be doing is stepping through this this website, essentially Zero to Jupyter Hub. So I recommend you have a look at that. It explains quite simply how to set up Jupyter Hub in Google Cloud or Microsoft Azure. I've not tried it myself on Azure, just on Google Cloud, but it's pretty easy to get going. Okay, so just to show you, this is my Google account. Ignore those two machines that are running there. That's just, I didn't do any tidy up. So for the moment, we don't have Jupyter Hub deployed at all. And I will just show you, I'll be working from the command line a lot. So just to show you, at the top there, that won't be visible. I essentially have a watch which is going. So for the moment we have nothing, so we just can't connect to anything. What this is trying to show is the number of nodes, that is virtual machines available in our Google Cloud. And then we'll be looking at the number of pods running. So this is running Google Cloud, so under Kubernetes. As Docker, the basic unit of execution is a container. With Kubernetes, the basic unit of execution is a pod, which is essentially one or more containers, all in the same network space. And then also we're showing the proxy that we'll be using to publish our Jupyter Hub server on a public IP address. Okay, so for the moment, there's nothing to see there, but we'll see that advance as we launch the system. Okay. Okay, so I said I'm going to be working from this site. There are several steps to this. So first of all, to create a Kubernetes cluster on our Google Cloud. Then we will set up a tool called Helm, which is part of the Kubernetes project. And it's a bit the equivalent of like Docker Compose you would have in a Docker environment. With Kubernetes, this allows to specify in a declarative way the components of your solution that you're going to deploy across a cluster of nodes. And then we'll look at how we can prepare the configuration file to then deploy Jupyter Hub. Yeah. Well, I mean, if you search already Zero to Jupyter Hub, I'm pretty sure you'll find it. It's Zero to Jupyter Hub. I mean, it's 0-2 Jupyter Hub. I mean, I recommend just looking up on Google. Yeah, so it's actually the readthedocs.io page is the one you want to get to. Okay, so I'll show how to set up a basic Jupyter Hub installation in Google Cloud, and then I'll just show how to deploy your own image, so to extend the basic configuration. Okay. So I should just say that with the Google Cloud, clicking up here, there's a console icon, very small up there, which you can click on, which will open a console. I'm not going to use this. I'm going to run these tools locally, but it's just to show you that this exists. The command line tools that we use, G-Cloud, G-Cloud SDK, and kubectl are automatically available to you in this environment. So just to show you that they're present, G-Cloud, and up. I wanted to X. Okay, it's better. Okay, just to show you in that terminal environment, you have those tools available. I have them installed locally on my machine. That's how I prefer to work. But you have that option. You don't have to install any tools then to do this procedure. Okay, so that's within my Google Cloud console. Okay, I've actually, the way I'm going to demonstrate this, I've actually scripted it up. And it's a good idea. That way we'll be able to go quicker. And that is, if you're interested, that's on this GitHub repo, MJ Bright, PyCon US 2017 theory, hyphen Jupyter Hub demo. But it's just implementing a lot of the stuff that's on this Read the Docs site. So that's really what you should be looking at. So we've seen the Google console. I've already locally downloaded the G-Cloud SDK, the one that's available through the console. And I'm going to use a command like this, larger, G-Cloud container clusters, create your cluster. So what we're doing here is we're creating a Kubernetes cluster, which means that, so we put num nodes equals 3, we'll create 3 virtual machines in the cloud, okay? And this will automatically instantiate that with a Kubernetes cluster for us. Let's see, okay. So this was all looking fine in my environment. It's going to be a bit trickier with on the screen, so I hope things are going to be readable. So I've got this script where I just do everything automated. So the first step is I'm going to run that G-Cloud command that we just saw to create an environment. Okay. So you can read that. Creating container clusters and giving it a namespace name, Jupyter Hub. Namespace is a Kubernetes concept. And setting them nodes equals 3. So that actually takes, I think, about a minute or two. So whilst that is running, let's look at what comes next. So once we've got our 3 nodes up, that watch command that I showed you up here, we should soon see that, at least we'll start to see the nodes. So these are the virtual machines of our cluster. And so it's kubectl get nodes, which is the command that allows us to interrogate those. I'm just running them here under watch. It's just cycling through. Okay. Okay. Go back to that page. Okay. So we've got our cluster in process of being set up. The next step that we will do will be to download the binary for Helm. As I said, Helm is a Kubernetes project that allows you to specify the components of your solution. Okay. And after that, we'll be setting up the configuration specifically for our Jupyter Hub application. Okay, still no nodes yet. So we download the Helm binaries, form a Helm init, not too concerned about those details, and then we'll start configuring some YAML files so that we can install Jupyter itself, Jupyter Hub itself. Still going. Go back to the Cloud Console. No, still nothing there either. Seems slow. I've done it about 5-6 times this morning. It's never failed me. So. Okay, so finally got our 3 nodes suddenly appeared there. So that's the output of our kubectl get nodes command. And if I go to the console, we should see, okay, these first 3 machines there are all labeled Jupyter Hub. Okay, so those are virtual machine instances. So we now have a cluster. Okay. So the next step is I'll download and install the Helm utility. In fact, I've already done that, so I'll just pull it down from that URL, which is in the Helm page. Perform the Helm init. We're not concerned about the details of that. We need to generate a couple of SSL keys that we will insert into a template config file. Okay, so using OpenSSL, I've generated these 2 SSL keys. SSL cookie, SSL proxy, and if you look at the template, so this is config.yaml template where we basically got a placeholder for the SSL cookie and placeholder for the SSL proxy. So we will substitute them in that template. That's the template with the keys substituted. And the next step is, so now we have our configuration ready to go, and we invoke Helm install. So we reference this URL. It's not very readable, it's not too important, but basically there is a long URL on GitHub that references what we call the Helm chart. Okay, so it's a file called Jupyter Hub version 0.3 tar.gz. Okay, so it's basically a tar file with a set of configuration files that describe how a Jupyter Hub should be installed under Helm, under Kubernetes rather. Okay, so we've launched that. That was a Helm install. Let's run. Okay, I'll have to make it smaller so you can see some of this information. Okay, so we're starting to see now pods that are being created. Okay, so you can think of them as containers. Okay, so we can see them in various states. The proxy is in running state. The hub deployment in container creating typically often means it's pulling down an image. And also it's created a public proxy, which means that we have an external IP address. So it's this address that we'll be using to connect to the Jupyter Hub console out in the Google Cloud. But we need to wait until the pods are ready before we can access that. Okay, looks like we're ready. They're both running. So pick up that IP address, go to my browser, it's not fast. Okay, sometimes there can be other things going on. So that is right. Yeah. It'll come. So whilst we're waiting for that to come up, if you think about what we've done so far, we've just with one command, we've created a cluster of 3 virtual machines in the cloud. And then we've just modified a template describing our configuration with a couple of SSL tokens. And with Helm, we've actually deployed the Jupyter Hub. So here it is now operational. As you can see, with very few commands, we were able to get Jupyter Hub up and running. Now, as Matthias mentioned earlier, of course, this is completely unsecure Jupyter Hub. We're using HTTP, and there's no real user password authentication here. We can just enter what we want as a user and password. On that 0 to Jupyter Hub, read the doc site, they describe how to go further to do Google authentication, for example. I'm not going to do that. There are other things I will do. So, okay, I just log in as a user. A, very imaginative. And we can see that we already got a notebook. I just want to go back here and just show that I logged in as user A, and we have here a new pod, Jupyter-A-1. So if I then add another, log in again as Mike, for example, we would get Jupyter-Mike-2, and so on. Okay, so what have we got? Well, we haven't got much so far. I mean, it's a typical Jupyter server. We see you've got Python 3, and we can start a terminal and stuff. Fairly classic stuff. Okay. So far what we've done, actually I could have a look at that. Is that one of you logged into my server? I didn't create that second pod, doesn't matter. Okay. Okay, it's not very readable, I'm afraid, with the screen size, but what I'm doing here is if I do a kubectl describe of the pod, which is one of those notebooks, which I'm going to do the one I created, which is Jupyter-A-1. So I do a kubectl describe, it will show me details, and it's just to show that we can see the actual Docker image that is deployed by default with this chart that we've deployed. Okay. So an interesting next step would be to change that image, put it's fairly basic notebook with Python 3. Let's see how we can start adding things in. Okay. So what I propose is we're going to take a Docker file, and we're going to derive an image from a Jupyter base notebook. This is one of the notebooks defined in GitHub and Jupyter Docker stacks. Okay. And we're going to create just a base notebook, and we're going to just copy in the IPython and Git repository that we've been using in the labs today. Okay. So this is a Docker file. from Jupyter-based network. I'm just setting up the work dir for user Jovian, and I'm copying in just a local copy of the IPython in-depth repository. So I do the Docker build on that. I'm doing it on my system with my username. It's gone MJ Wright. Oh, see it at the bottom there. So we've built that container, and now we're going to push it up to Docker Hub. On the 0 to Jupyter Hub, they use the Google Container Registry, which you can do. I chose to go with Docker Hub. Okay. And I've been doing this all morning, so there's only just that one layer that it has to push up to Docker Hub. Okay, so I've got my Docker image out in Docker Hub. Now I want to add a section to my config.yaml, the file that's going to tell Helm how to configure our Jupyter Hub. And I'm going to add this section referencing my image in Docker Hub. Okay, so I now do a Helm upgrade. Previously, we did a Helm install with Jupyter Hub and with our config YAML file. Now we simply do a Helm upgrade. And we should see things start to happen up here. Okay, so you can see we have some, in fact, we have 3 pods called pull latest something. So this is clearly a pod, 1 per node, which is pulling whatever image layers are necessary for our new service. By experience, when these have terminated, which is fairly quick, I think, we then get a change here. We have to wait a while for the new hub deployment to be ready. Okay. So that was the old hub deployment we had, which is terminating, and we have the new one, which is creating. I think that takes another minute or so until that's running. So it's interesting to see we've changed the base image that will be used when we launch new notebook servers, okay, new Jupyter servers. So if we log out and log in again, sessions will be using that new image. But the current sessions we already have continue to run all the same with the old image. So what I'll do after this next step is I'll do another just example of modifying the image. I'll go for a larger notebook image, not much larger. That base notebook is about 280 megabytes, I think. I'm going to take a minimal notebook, which is about 900 megabytes. Okay, so our hub deployment is running now. So I can go back here. I can log out. Let me log in as Mike. Just change. So we see Jupyter Mike 3 now, new session. And if we look here already, if I do so I do another kubectl describe pod, just so that we can see that we're now using this new image that it's pulled off Docker Hub. But much more obvious is when we actually go okay, yeah. When we go to the notebook itself, the Jupyter server, we see that we have the IPython. Oh, sorry. There you can maybe see we have the IPython depth stuff copied in. Okay. Okay, so just an example of customizing image, having stuff in. I'm going to go to a third example. So as I said, I'll go to a minimal notebook image. This is something that's 900 megabytes. Personally, I like Bash kernels with Jupyter. I do a lot of stuff with Bash under Jupyter. I do Docker tutorials and stuff. So like yesterday, we were doing some stuff in Python for Docker, Kubernetes, and Mesos, and some other stuff in command line for Docker, Kubernetes, and Mesos. And I find Jupyter really useful for that, for documenting a lab, and you can run it from start to finish, check that everything's still working. So I'm a real fan of the Bash kernel. So here's a Docker file for this third invocation. So you don't see the first line here. There's a from minimal notebook. Set up my work there. I have a requirements file which just specifies Bash kernel. There's a command to do, the pip install that requirements file, and then a command to actually install the Bash kernel. And I copy in just a skeleton example of some sort of Bash arrays tutorial, just to give it some meat. So we'll build that new image. So we'll build a new image, we'll tag it as we did before, and I'll push it up to Docker Hub. Okay, a new image is ready, so we'll push it up to Docker Hub. Go very quickly again. Now we modify again our config.yaml to reference this new image, which is in Docker Hub. And then we'll do a Helm upgrade again with our modified config.yaml. So you can see now I'm referencing this new image, MGBright, with my min notebook. It's not the same one as we were running before. Okay, so that's going to take probably a couple of minutes yet for that to deploy. We've got those 3 pull pods still running, and after they've run, then we'll roll over to the new hub deployment. Let me just mention in that 0 to Jupyter Hub read the doc site, they mentioned a tool called source to image, part of the OpenShift project, which is essentially Red Hat's Kubernetes distribution. It looks quite interesting. You can do the same sorts of things that I'm doing explicitly with the Docker files. So let me go to an example somewhere. Go back here. So I actually tried it in the last hour or so and failed, but it's the first time I use it. It's interesting to see it exist. But the basic idea, so this is called S2I, source to image. You can download a binary for various platforms. And essentially you do STI build. You can provide a GitHub repo where the source is for the image you want to build. So in fact, I wanted to use, there's Git repo, Jupyter, Docker demo images. It builds the image which is used for try.jupyter.org. I've always liked that multi-language demo image. So you provide the URL of the source. You provide the name of the base image. So although there's a Docker file there, it doesn't actually take the base image that's in Docker file. You actually override that. And then you give the address of the Google Container Registry to upload your built image. Okay, so yeah, I tried this earlier on the Docker demo images. It was failing for some reason. It was a first attempt, so I just tell you the tool exists, and it looks pretty interesting, worth a look. Okay, I expect this is finished to deploy now. Yep. Oh no, container creating. Should take another 30 seconds or so to complete. Yes. So it's in fact, one pod, which probably has one container, and that container is a Jupyter Hub server in a container. Jupyter server, sorry, in a container, not Jupyter Hub. Yeah, for every login, yeah. Okay, we're coming to the end of the session. I'll come back to that as it completes. Are there questions about what I've shown? Are any of you deploying Jupyter Hub already, maybe in a classroom environment, or want to? No? Okay. Anyway, I think it's pretty cool that they've made the Zero to Jupyter Hub site available. I know that last year I presented at EuroPython, in fact this tutorial, more or less, but not at all about Jupyter Hub, and there are quite a few people interested in how to deploy Jupyter Hub, which I think was a more difficult task a year ago. This seems to make it a pretty easy thing to do. Okay, so that's running. Where was I? Oh yeah. I'll do a log out, that one, and say Mike. No, A2. I mean, it's the equivalent of what we saw before. This time I've just modified, so we now have in the kernels we have a Bash kernel available, and I have an example notebook, which in theory is a tutorial on Bash arrays. Because I reckon Bash deserves some love. Okay, so the first thing I do is just some magic to see what system we're running on. So this is actually a Debian Linux, and the Bash version we're running is 4.3.30. I mean, if there was a real Bash tutorial, you want to know what version of the OS, what version of Bash you're running. And then the content of that is not too important. It's not even finished, actually. I should go back and finish that sometime. But, okay. So I just wanted to show you how easy it is to deploy Jupyter Hub in your own Google Cloud account, and then how easy it is to modify the images that will be presented to users. So I encourage you to look at the Zero to Jupyter site, remembering that, of course, this is not a secure implementation. In the site, they describe how to do proper authentication, which is something you would definitely want to do, especially in a classroom environment. Okay, it's time. If there are any questions, I'm available. Whatever. it will have its own copy of files. Yeah.
So you can, if you look at the config file, you have storage equal null.
Hmm.
So it was just inside of the container. You have ways of mounting things. Like everything is an option. Like the
Yeah.
application